Okay. Right, let's see how it goes. We have two parts. One is lessons. The other one is you want to test today?
A test?
Yeah.
I remember this.
Yeah, it's on the covalent substances. Let's see how it goes. You're not ready? No. So when are you going to be ready? Next week we don't have a lesson. Okay. Next week is a break. So you have a good break to rest. All right. Anyway, let's see how it goes first. This chapter is chapter 3, which is on metals. Metal is a pretty small chapter. The main focus, most of the things you had learned, you have pretty much have learned it in those secondary level chemistry or like in science. But I'll be focusing a little bit more on linking of different concepts here. So that especially when you are trying to describe those properties of metal in terms of the structure and then their metallic bonding. Okay, metal itself is an element. Then you may be wondering, why do we need to have a bonding in that metals? Because of its nature and property and the structure, they do have a bonding, but it is not that that particular metal is combining with, that bonding is not between the metal itself and then the other one, it's between the structure itself. Okay, and that is one particular area where we are going to look at and link that structure with their metal properties. That is a one main point. Second point is about their extraction, but we are not going to look at extraction in details because this is not part of your study design. But what we are going to look at is the environmental impact and other impact based on their production and extraction. Okay, so these are the two main areas that we're going to look at. One of it that we are also going to look at is what we call it circular economy, which is one of the main theme of your study design. In your school set, then this is the very first, normally the very first practical or like probably the report that they want you to create based on that circular economy. Okay, so we're going to focus these two main things and let's see how it goes. If we have too many absence, probably we'll do the test on the week after. Okay, happy?
Yes.
Okay. Because somebody seems to be just wake up from yeah? Yeah. No, not really. You just wake up? No. Okay. Because holidays as usual, right? You can sleep like until like you save breakfast, you save lunch, you eat only dinner. All right. Anyway, okay. So let's look at this. Generally, what we are going to look at is the structure and properties of metals. So this is what we are going to look at. Very first thing is, of course, we are going to look at that a particular properties. Okay, so properties that we are going to look at is what we call it ductility and malleability, luster, and good conductor of electricity. Okay, so these are a few points, and then they also have a high melting point, and then ability to conduct. These are a few, or rather, all the properties that we are going to focus. A few example is given, a few definition is given here. So it's the ability of a material to be drawn out into a long wire. Malleability and ductility are different. Ductility, malleability is its ability to be able to, sorry, what is it? Its ability to be able to apply the force without breaking it. So it's distorted by an applying force without breaking. So these two are quite similar. So ability to form into different shapes. Ability to form into different shapes. Seems like I can do the test today. Ability to change into different shape without breaking is a malleability. Ductility is like when you stretch. Okay, so it's ability to stretch it into a long wire. Lustrous, of course, you know that its appearance or surface, it's reflect the light. Lustrous material appears shiny. Okay, then we are going to look at why, what is the reason why there is a shine, that particular shininess or shiny thing is all about. All these properties actually boils down to one main point, what we call it, due to its metallic bonding. Okay, the main purpose is, of course, all atoms prefer to have a stable outer shell electrons. So that is usually what we looked at. So we need to have a stable outer shell electron configuration, which is either a 2-electron or 8-electron. In metals, it's also no different. They also want to lose their valence shell electron to form their outermost shell to be either 2 or 8. Of course, we only have a one metal which will have a 2 electrons in the outermost shell, which is lithium. Other than that, the rest will have 8 electrons in the outermost shell. So when they lose electron, they will form an ion, positive charge ion called the cation ion. Why is it called cation ion? Because it looks like a cat. Does it look like a cat? No. Why is it called cation ion? Anyone has any idea? A cation ion is something that go to what we call it cathode terminal. It's like electrolysis, because the purpose of it, it's cathode means it's a positive negative electrodes. Okay, so because positive ion will go to negative electrodes, and that's why it is called cation. And they will always form a positive ion. So this is cation ion is generally a positive ion. So in a metallic substance, this process will generally leads the production of many cation ion. So when you pick up a piece of metal, that piece of metal, almost all the atoms will lose their outermost electrons to make sure that they form cation ions. For example, like if you look at magnesium, its structure is 2H2. So in this case, in order for it to be stable structure, it will lose these 2 electrons to form 2,8. So it will lose 2 electrons by forming magnesium 2+ ion, and then 2 electrons will be like wandering around in the structure without related to or like stick to any of the ion. Okay, so that we have so when in the metal, pure metal, or like just a metal piece of metal, magnesium atoms will not be staying as a normal magnesium. It will split into a magnesium 2+ and then 2 electrons. So where will this 2 electron go? This 2 electron will be forming something called sea of electrons, and you will have a positive ions. Okay, so that is generally what is going to happen in most of the case. So let's look at this. This process leads to the production of many cation ions and free electrons. Cation ions are in a solid, those cation ions cannot move because it's a solid itself. They will stay in the structure. Okay, so which means that this particular cation ions remains in the solid structure, while those ion electrons that come out from those metal atoms to become cation ion will be wandering around. Okay, So this is what they say that here, they can move around freely in the middle. They are not associated with any particular actions. And what happened now? You guys, this particular piece of metal has negative ion, or rather positive ion, and then electrons, sea of electrons. So this metal is being bounded or like being pegged with a strong electrostatic force of attraction. What is the electrostatic force of attraction? Is the attraction between this cation, which is a positive ion, and this sea of electron. It's like something that is being wrapped with a wrapping paper or something. Okay, so that makes it to have a. This part is important. You need to know. So this, the electrode. This highlighted not use. Okay, then I don't use angry. Okay, so the electrostatic force of attraction of these negatively charged free electrons to the positively charged cation is the basics for metallic bonding and holds everything together in a regular structure called crystallic structure. This statement is important that explain or define what is metallic bonding and what is so special about this metallic bonding. Even though we have known that covalent bond is formed between the two when you are sharing two electrons from two different atoms or maybe two atoms, but here they are not sharing to form. It's just that they will form cations and electrons. They will attract each other. Okay. Yeah. So that is about metallic bonding, and you should be able to draw this particular structure. Okay. You should be able to draw what do I mean is that, okay, let's say if I ask you to draw how does a lithium atoms or lithium metals look like, then you should be able to say something like, okay, I have a lithium, and then you have a plus, another lithium cation, lithium metals look like, or we have another lithium. So each of them is represented as a positive cations of lithium, and then because each of them will lose one electron, so you will have something like simply 3 electrons wandering around. That is something like a very simple lithium metallic bond structure. Somehow is if they ask about aluminum, if they ask about magnesium, if the question asks you to draw a metallic bonding structure or like crystallic structure of any metal, you should be able to draw like this. You have a cation with a free moving electrons. All right. Questions so far? Are you okay? All right. Yep. What is the cation? The what?
The delocalized like
Yeah, floating around.
invalid.
No, it will be overall is balanced normally. The overall charge is still 0, but it's just that those free mobile delocalized electrons will not be stick to any particular atom. They are able to move around. Yeah, that is also another reason why the metal have that lustrous shapes. Lustrous, this shininess actually comes from those electrons. Yeah. Okay.
Which of these boxes, if you draw the wrong amount of
Wrong number of, not really, because when you look at like number of electrons is not so important. The thing is that those electrons will come from the cation, which is not drawn here. So the number of electrons is not important, as long as you have electrons and then cation, that is good. The property of the metal that allows them to be formed into a wire, what is it called? Ductility, right? Ductility. Ductility or ductile. Other than your answer in question one, list three other common properties of metal. What are the three other common properties? Lustrous. Yes. Yeah, conduction. Conductivity of electricity. And we also have a like high melting point. Okay, what is basically a metallic bond? How do you define a metallic bond? Then, yeah, it's basically it's the attraction. So we call it electrostatic force of attraction. Between the cations and C of delocalized electron. Sorry, delocalized means they do not stay in their location. Why do metal atoms form cation, not anions?
Better lose, better gain.
Better.
Better lose, better gain. They lose
Stable electron, yeah, so they need to lose electrons to get a stable electronic structure. So probably we can say something like they need to lose electron to obtain the stable electronic structure. All right, good. Okay, now we are going to explain on the properties of metals, and we are going to link that with why do they have these properties, based on their metallic bonding. Okay, so metals are malleable, so they can actually deform into differentiate without breaking. It's different from elastic. Don't say elastic. Elastic and malleable, are they the same? No. So what is the difference? When you say elastic, what does it mean?
Stretching.
It can also be stretched.
It goes
It
back.
goes back, yes, that is most important thing. Elasticity is something that when you apply a force, it will stretch, it will deform, but when you remove the force, it will go back to its original shape.
Could you say like, it has potential energy? Like,
It's an elastic potential energy when you stretch one while it is being stretched. So when a force is applied to the metal, such as when it hits with a hammer, the cation and a sea of delocalized electrons are able to shift. This is the key information. Sea of delocalized electrons are able to shift. Cations are also able to shift because they are arranged in regular pattern. Okay, so they are arranged in regular pattern. Your internet connection is unstable. Okay. Okay. Arrange in regular pattern. Yeah, it's for cations. So it's like layer. When you strike, they will actually be able to slide. Okay. And the localized electrons are able to shift and still maintain their attraction to each other. If they can't maintain their if they can't maintain their attraction, what will happen?
Break.
They will break, yes. So this is what happened with non-metals. The non-metals are fragile. So when they apply a force, they may be able to change the position, but they will break. Yeah. It's like regular row. It's rows and columns. Yeah. What happened? Internet connection. Let me share the screen again. Okay, right. Okay, so main reason when if they ask why metals are malleable, you should be able to answer this two statement, this two sentence actually gives you the reason. So you should be able to answer the reason. If the reason must contain two main parts, one is ability for them to shift, but after they shift, they should be able to still maintain their attraction. If you don't include the second part, you do not get half of the marks. The first part is half of the main reason. Second one is you still need to mention that they still maintain the attraction. All right. All right. Next, metals are ductile. It's the same reason. Ductility and malleability in terms of their property is still the same. Okay, but it's just that ductility is changing the form into like a shear force. But this one is like stretch into a spring. It's like essentially the same for this. But the other one is metals are good conductor of heat. Why are they good conductor of heat? Because delocalized electrons are able to move freely throughout the lattice structure. Lattice structure means that just now the structure, the regular arrangement structure is called lattice structure. Okay, when heat is applied to one part of the metals, electrons present will absorb this thermal energy and transform it into a kinetic energy. So kinetic means movement. Okay, so they will start to move faster. This is the move fast. Move faster. This. Move. Look here. Okay. Okay, so when they will move faster around the lattice, going from hot end to the cool end. Going from hot end to the cool end. This way, electrons are able to quickly transfer the thermal energy through the metal, which is what makes metal good conductor of heat. So this is about heat. The conductivity of the heat and the conductivity of the electricities are different. You can't use the same way to explain. Conductivity of heat is when you heat one part of the metal, the electrons in that particular part will start to move faster and they will move through the lattice to the other side, so that when the electron reach to that point, that end will become hotter because electrons move very fast in that. And of course, you will not learn particularly here, but if you are taking physics, in physics, you understand that kinetic energy is related to heat, okay, or rather temperature. Okay, metals are good conductor of electricity. Electricity is the movement of charged particles through a substance. We are explaining this because in case we are doing chemistry, so it's trying to give you a definition of it. So importantly, when it comes to metal, we know that lattice contains sea of freely moving electrons. Therefore, these free electrons are able to carry an electrical current throughout the metal. So that is the main reason why they are a good conductor of electricity. Yeah, question.
It's like the heat, it transfers the heat to the electron.
When you heat one side of it, electrons in that side will gain kinetic energy, so they will move faster. So when they move faster, they will not stay in their position. They will move, they will actually what we call it spread to the lower portion. So if you see that, okay, in any event, if you see there's a lot of people crowded and moving around, will you stay there or will you move to the point where you have a lower movement? So that's how they do. So they will actually move to the other portion, which is the cooler portion. That makes it a conduction.
Is it like contagious?
Yeah, it's like something contagious. It's like move. Yeah. So when the electrons move to the cooler end, it carries that thermal energy with it.
Does it just travel that way?
Yeah, it will travel that to the cooler side. Yeah. Why?
What does it go to?
That's what I'm trying to say. Is like, would you stay in a very crowded and like in dynamic place, or will you go to the place where you have a less crowded? It's like, okay, if I ask you, you know diffusion? The smells. So when your mom cook in the kitchen, how do you get when you're sleeping and then you get a smell and then you get wake up, right? How do you get that smell? It's a diffusion of your smell particles, right? From the air. Then your mom cooks in the kitchen, and then how come it's reached you? It's coming from that portion, yeah. It's because of that. Okay, metals have a high melting point and of course boiling point, but we are more particularly important this. So of course, cause the cation no longer to be held within a regular unit structure. That is what we call it melting point. Okay, melting point is the temperature that cause the cation to no longer be held within their regular lattice structures that makes them to melt. But if they have a strong electrostatic force of attraction between the cation and the device, this is very strong. So that means this statement is important that a large amount of heat energy is required to disrupt these force of attractions. That's why they have a high melting point. If you just said that this is strong electrostatic or metallic bonding is strong, it is not good enough. You need to explain why this strong electrostatic force leads to requiring large amount of. That's the reason why they have a high melting point. Is that clear? What I'm trying to give the reason, when you give a reason, yeah, you will keep on saying there's strong electrostatic force of attraction, strong, but that is not just good enough to explain here, because melting is like sort of like disrupting of the structure. But for you to disrupt the structure, you require large amount of energy. You need to mention that you need large amount of energy to disrupt. That's why it's up. All right? Are you okay? Questions? All these I'm sort of like they were somehow asked somewhere to ask you to explain why they have this particular property. Again, last stress, yes. They said that free moving electrons on the surface of can reflect light. So there are many delocalized electrons moving freely, they are able to really reflect the light. So when you look at the metal, why do they are shiny and slide light? Because of those moving electrons. So many of them, billions and billions and billions of them inside. Okay. Yeah.
So the electron.
Collectively, yes. Because its amount is the number is so huge that actually have the same effect. You think that if a metal piece of metal, okay, if you look at this, it's metal, right? So if I tell you that, you see that one is like a solid. Solid means nothing is moving. You think it's nothing is moving. No, there's lots and lots of electrons are moving around. So that's why you find it this kind of. Never thought about it. Oh no, I mean, okay, if you look at the water surface, it's like sparkling like a water surface and then like normal like water surface when it's still, which one looks a little bit more bright when it's moving, right?
Oh yeah.
Yeah, that's how it works. Okay, right. Next questions. Let's try to answer. Using a metallic bonding model, explain why metals are good conductor of electricity. So it's a movement of electrons. Okay. Really movable, delocalized electron. Yes. Large metal structure. It's the main reason why metallic bond model explain why metals are good conductor of electricity. Provide an example of property that metals cannot be explained using a metallic bonding model.
Wait,
Charges and move throughout the metal structure. So it forms a current, right? Okay. Can you think of any properties of metal that cannot explain using metallic bonding model? Which one? Melting point, I thought we mentioned one. What about magnetism? or sonorous, making sound.
Feel like the attraction between two different
But can you explain how does it make sound?
sound.
Yeah, sonorous. How's metals are sonorous?
Vibrating.
But is it not nothing to do with a metallic structure, metallic bonding, right? It could be the property of sonorous, magnetism. You can't explain using a magnetism. Because actually magnetism is due to the electron. It's because of the electrons also, but it's a different nature of electrons. Because when the magnetisms, okay, for your information, why magnetism comes about is for any atom you have a nucleus and then electrons is moving around. Electron is moving around. So if the electrons move, each atoms will be acting as a small magnet. Any one of you taking physics in school? No. Okay. So it's called a right-hand rule. So when the electrons actually move, this will form like a small magnet. So each of the atoms have its own small magnet. So when they combine together, they will form a what we call it magnetic domain. That magnetic domain, when they align, it becomes a magnet. So any metals that have an ability for their magnetic domains to be able to align, then they will are called magnetic material, but which is nothing to do with this bonding model. So magnetism is one thing. The other one is sonorous. Sonorous. So it's called making sound. Yeah. So these are some of them. Explain why it is unlikely for the oxygen to form a metallic bond. Yes.
Electrons to gain.
Yeah, it gains rather than lose, right?
Because
Yeah, it's a anion. It will form anions. So it cannot have like those electrons. So because metallic bond require cations, but oxygen forms anion, which is a negative ion by gaining electron. Gaining. And then you see, so that could be the main reason. Okay, so this is what they call it, draw a fully labeled diagrams of metallic lattice for aluminum. Aluminum has 283, so it will lose 3 electrons. So generally, you do not need to draw too many, maybe 2 layers, 2 rows of, you can just draw like 2 rows or 3 circles, maybe 6 should be good enough. They must be regularly arranged, and this will form Al3 plus. So Al3 plus Al3 plus Al3 plus. Ideally speaking, when you lose 3 electrons, they should have a 6 times 3, 18 electrons outside. So when you draw, maybe you can randomly draw 18 electrons. But even if that electrons are not exactly 18, that should be okay, because it's quite random that they are freely moving. Right. You should not be drawing the electron which is very far from the structure itself. So we can see that this one is localized. Delocalized electrons. Magic. This one is what we call it cation. Sorry?
Well.
No, must be 3 plus because you need to know that it's going to form a cation of 3 plus. All right. Copper is commonly used for a variety of different applications. For each application, you will state an explain the property that makes it suitable for its use. Base of a fry pan. So, good conductor of heat, right? Good conductor of heat, as well as high melting points. Electrical wiring, good conductor of electricity. Water pipe.
Would wire those be?
Water pipe, malleable, because flat and then curved. Malleable. Or malleable, it doesn't matter whether it's adverb or adjective side. They don't care about property. I think it must be adjective, right? Okay. B is about their reactivity. We can look at their reactivity. So all of us agree that you're going to do tests next week, right? No, I mean the following week, right? Not this week. Oh. But don't be absent. Okay. So I'll just continue. Okay, otherwise I'm going to start. No. In holiday, don't want to do that. Okay. Let me double check that just want to make sure that it's not being sent to everyone. One minute break. No. Okay, can have a very short break. Okay, we'll do the test on the following week, okay? Okay. All right. Next part is about reactivity. You have learned reactivity series before. Some of you may, some of you haven't. In secondary science, have you learned reactivity series? No. Reactivity series means how reactive the metal is. Okay, so one of the most reactive metal is something like CHEM or francium. Francium is actually the most reactive metal on Earth, but sadly, at any one time, okay, at any one time on the Earth crust, in the Earth crust, there is about only 3 to 4 grams of the francium can be found. Because it's very radioactive, it will be like breaking up, then forming. It's along the way. So francium is a very rare earth metal, but you can't even find. But the nearest one is cesium. Cesium is the most reactive metal, but it's also hard to find, so we can't use it. So in the lab or like in school, the most common metal that is the most reactive that we can find is potassium. Okay, don't ever try to put a potassium into a bottle of acid. It will break and shatter and then have like a kind of like small mini explosion. All right, but anyway, why some metals are more reactive than the other? So we are going to explain, of course, based on our knowledge from chapter 1 as well. Okay, so one thing is that as you look across the periodic table, the atomic number increases. However, the other atoms tends to exist within this. So that is the reactivity of the metals. Okay. When metal react, they must lose electron. This one is important. So therefore, the reactivity of metal can be thought of as how really a metal loses electrons. Its ability to losing of electrons. If easier to lose electron, more reactive. That is a relationship between the ease of losing electrons and then the reactive. Okay? So they say that the more easily a metal loses an electron, the more reactive it is. So which is also relevant to something called ionization energy. Okay. All right. So as a general rule, metal increases reactivity of metal increases going down. Okay, that is for metal. Okay, only for metal, not for non-metal. So do not take that. Okay, now we have learned that if you go down the group, reactivity increases, not for non-metals, only for metals. Okay. Only for metals. As you go down the group, it is reactivity increases. Okay, if I'm going to look at like blue one, potassium is the more reactive than sodium, and cesium is more reactive than potassium. Because as you go down the group, what's the main reason? You need to know this reason. You need to remember this one. You should be able to write down. As you go down the valence shell is further away from the nucleus. Okay. So in this case, they have a less electrostatic attraction to the nucleus, therefore more easily removed. So that's a more easily removed. That's the reason why, as you go down the group, the reactivity increases. Reasons, these are the reasons that you should be able to explain. 2 points. Valence shell electrons away from the nucleus, less electrostatic force of attraction, so it's easily removed. Okay. So that's how it goes. So it's much easier to remove these electrons compared to this. So cesium is more reactive. What about across the period? Going from left to right, it will be lesser. Move across from left to right, reactivity of metal decreases. This means that sodium is more reactive than magnesium, which is more reactive than so on and so forth. The valence shell for all three atoms in a period is the same shell. So as you know that the number of shell remain the same, right? Then the thing that does not change as we move across a period is the core charge. Core charge is constant. This one constant. Oh no, core charge increase. What do you mean constant? Increases. Then increased core charge means the atom will less readily reduce and will therefore less reactive. Because if you look at here, the core, this is 11. So the core charge here is 11. This is going to be this is sorry, this is wait, what did I write down here? Valence shell for this is the thing that does not change as we move. Why do I put increases here? Core charge. This. Actually, core charge is not the one, it is actually the size. Why do I put a core charge? Let me think about it. So valence shell is the same. Does change as we move across this the core charge increase. Does the core charge increase across the period? Yes? No? Yes? From left to right. What is core charge? What is core charge is the number of protons in minus away the valence electrons. Yeah, so it gives you the, it increases, right? What is the core charge here? +1, right?
Yeah, to left to
Yeah.
right.
This is +1, right? This one becomes +2, right? So this one becomes +3, right? Okay, core charge increases. Core charge is the same as your number of valence electrons. All right. No, it's the only thing wrong is here core change, not core change, core charge.
It's just
This one. Core charge. An increase in core charge means the atom will less readily use electrons, so therefore less reactive. No, that's fine. So this one is characterized by the way that it can react with cold water and hot water. If you look at like potassium, sodium, which is in group 1, okay, it's able to react with cold water. But things like magnesium, zinc, copper, gold, which are on the right side, will not be able to react. And same thing like in hot water, potassium, sodium, magnesium, zinc is able to react, but copper and gold cannot. But this one I will discuss a little bit more details later on. Okay, for the reaction of metal with acid, this one is one of the main probably points that we are going to look at as well. We can use the production of hydrogen because any reaction of metal, okay, maybe let me try to explain what does it mean. So metal, metal plus acid, it will produce salt plus hydrogen. So hydrogen gas is something that it will be if it reacts, yes, if you are using what we call it dilute acid, it will not react. It will not react if it is something like copper and below, but we'll talk about that one later when we do look at the reactivity in details. So the amount of the hydrogen gas released, the bubbles that forms, tells you whether that metal is reactive or not. If a metal is reactive, it will be able to produce lots of bubbles, whereas a lesser reactive metal will be producing lesser amount of bubbles. Right? In the same volume and concentration of hydrochloric acid, more reactive metal will be able to produce more bubbles. So it's not quite easy to monitor the equipment using reaction of metal with oxygen to determine the relative reactivity of metal. However, one method that is it's a bit rare, but what we can do is we hold those small pieces of metal with a Bunsen burner. When the reaction takes place, a glow will appear. So this is a reaction of metal with oxygen. That amount of the glow, the brighter and larger the glow, the more reactive the metal is. So that is a observation that we can make for the oxidation reaction. So it's, for example, like magnesium will glow so brightly with the Bunsen burner flame that you shouldn't look directly at it for too long. Zinc, on the other hand, will barely glow. Do you know where the magnesium is used? Mostly. Magnesium compounds are used in fireworks. That's how they produce the. Okay, these are comparative lists. I'm not putting a name, but I believe you are able to figure out what are the names for some of them, common one. You don't need to know all of them. Of course, cesium, potassium, you know, rubidium also, you know, right? Sodium, lithium, barium, calcium, you know. If you do not know strontium, okay, strontium also, but if you do not know, it's fine. But comparatively, this is how they behave in terms of their reaction. So especially like those very reactive metal will react explosively with dilute acids. But for the calcium, it will react less vigorously. This table just gives you a normally the one on top are more reactive than here below. Okay, so it's just a classification. Just take note about this strong reaction, violent reaction. Use the correct words like to describe. React explosively, less vigorously. They will react oxygen at the ordinary temperature. That means if you leave it outside, they will react. For example, like sodium or like potassium. Today that you are so happy, okay, I've got some money to make or maybe I want to do an experiment. You buy a piece of potassium, okay? Then you put on your table, you go to sleep. Morning, when you wake up, you can't find it anymore on the table. You only see a white powder. What happened? It react with oxygen and gone. So how are you going to store this? Those very reactive metal you have to place inside a piece in a wall. You have to place it inside wall to make sure that it doesn't react with oxygen. So when they store, you have to store with a box or like in a bottle. Okay, you may also see those things in your school. Those sodium and potassium metals must be stored in a wall bottle. Wall bottle, yes. And when you take out, and then you can cut with a knife. And it's like your rubber. Sodium and potassium, they are soft. You can cut with a knife. But those less reactive metals, they can only react with oxygen on heating only, carbon monoxide. So that gives you the two groups of metals. The one in the first row are more reactive. These are less reactive, and then these are like least reactive. So it's a strong reaction with hot water, moderate reaction, and not react with water at all. So that means whether it's a hot or cold. Same thing, vigorously with dilute acids, moderately with dilute acids. And something like this, like lead and copper, they will only react with concentrated acid. This is something that you need to know. They only react with concentrated acid. It's actually including copper. Copper also react with concentrated acid. It doesn't react with dilute acid. So if you are given an information that a particular metal that react only with concentrated acid, it must be copper. Any question? All right, so let's try to answer questions here. When a metal reacts, does it gain or lose electrons? I think it's quite obvious. Yeah, can you try to answer it? I have been answering the first two. This one is your turn. Okay, please give me a second. I'll be back. Please try to answer this. they lose electron, right? What is one way that you could measure the reactivity of metals through their reaction with water? How would you measure? There are a few ways to do it. If let's say like the metals are like very much different in their reactivity, you can measure whether a particular metal will react at a different temperature. The one which is able to react with a cold water will be the most reactive, or hot water will be less reactive. Some metals can only react with steam. So in this case, that will be least reactive. Okay. Or another way is how fast like the same amount of metal would disappear in the cold water. For example, like if both metals are able to react with cold water, then you will leave them the same mass, maybe the same volume, or put it there in the same amount of cold water and see how fast it actually disappear. Okay, so these are the ways. So generally what we can see is for this type of questions, compare the temperature for water which the metal can react. The metal that react with water at lower temperature is more reactive. That's something that you can. Or in another way that we can, another method that we can use is something like even for the same temperature. If a metal, or maybe we use like same amount of metal. Metal that disappear faster. The same temperature of water. Temperature of water is more reactive. Can I move on? The following qualitative observations were made by the scientists when adding metals to a solution of hydrochloric acid. Use this in order to order the metals in terms of increasing reactive, increasing. So which one is the least reactive? Copper. Next one is iron. Yeah, magnesium. Describe how this determination of reactivity in part A, how this determination of reactivity in part A was. Yeah, it's basically it's the amount of the bubbles that appear. Uh,
Is iron.
amount and the rate. Amount, rate of the bubbles. I think rate will be more suitable, I think. Rate of the bubbles.
As in like the speed. How they appear.
The fine reactivity series as is related to the metals. Actually, that particular series is from is arrangement of metals from most reactive. To least reactive. You know the order. You haven't right? Okay, maybe I'll write down in symbols. You do not need to know by heart, but anyway, this is the reactivity. What do you like the space here? Another one. I will write down later. Give me yes. So normally this is the most common one. And the space are for the position of what we call it non-metals inserted, which is one is carbon, this one is hydrogen. The presence of carbon and hydrogens will be discussed. Okay, especially hydrogen. We know that anything on the left side of the hydrogen is able to react with acid, dilute acids, or rather is like somehow. Anything below this, they will not be reacting with. Actually, it's a reactivity decreases here. This one is a decreasing reactivity from left to right. Is decreasing reactivity. Carbon precision of carbon is for the what we call it extraction method. We'll talk about that one in the part 3C. I mean, we may not have much time to go through everything there, but we'll talk about how we are going to extract extraction methods.
Is it for decreased reactivity for
All the metals. I mean, potassium is more reactive. So that means if you compare from left to right, left is the most reactive, right is the least reactive. No, it doesn't matter whether it's acid in general. It can be with anything. There is a kind of like a way to remember it, but of course in your study design they do not need you to remember it. That's fine, because this one they are going to compare this sort of like reactivity more detail in unit 3 when we talk about oxidation reduction. Okay, redox reactions in the galvanic cells, electrolytic cells. Is there all of it? Not all of them, it's some of them. Okay, so this is for 3A and B. Part C is I think is quite straightforward. I do not have much thing to say in part C. They are going to look at how metals are being mined and extracted. So depending on the location, normally metals are, I would say that it depends on the location of those metals. Some could be on the surface. Some are even like coming together on the river, in the river. So they do what we call it. I'm not sure whether you have seen, like they try to use pen to get some gold. If you go to like in a very in some certain area, you can use panning methods to get deposits of gold. Because gold is quite heavy, highly dense. So even like they use those what they do is they will actually grab like maybe a loads of what we call it, those clay or whatever is like things. You put it and then put it in the water. So the rest of those which are like less heavy will go away. The remaining ones is the most heavy one or most dense one, which is normally the wood. So that is what we call it pen method. They use the swirls and then. So penning technique is used to search riverbeds for gold, which is very common. And for those other metals which are less, I mean, okay, normally this penning method is used for least reactive metals because they do not react with anything. So when you get like this yellow color by itself because gold will never form a compound. If like things like gold, platinum, they won't form compound. Other metals just below the surface, if then they use an open cut mine. So they just scrap it from the top. Soil layers are removed and then underlying rock layer is blasted such that it can then be easily removed by trucks. Then this may uncover the sources of interest. You don't really need to know these methods, it's just a general explanation, but these methods will be linked to the environmental factors. For those who are further down the surface, like zinc, lithium, that they have to do is they go through the mine. So they have to dig underground mining. They use a shaft to drill into the ground to break depth. Then metal is located from this point. Mine is dug through horizontally because they will exist in the layers. Okay, transfer back to this. Okay, this part is important. What are the problems with mine? The negative impacts on the environment. Okay, so generally these includes the clearing of lands used for mine, deforestation, environmental impact include loss of plants and animal lives, decreasing biodiversity of the area. We can sometimes ask questions relevant to this. Mining also results in a significant level of air and water pollution. and water pollution. So these problems, these are the main factors that will ask us to do metal recycling rather than like extraction. So the method that we use for extraction will also depends largely on the metal reactivity and position within the reactivity series. And reactive metal found in the crust naturally. Those mines, when metals are mined, they are often not found in the pure metal, so they are found in ores is like a mixture of their compound. So pure version of metal, they use of extraction methods. Involve different magnets such as heating with other substances or undergo various chemical reactions. We are not going to like discuss very details about the extraction methods. One method that probably we can look at is this what we call it smelting. From other impurity by melting them at this process you need to. Doesn't want me to continue. So separating metals by melting them at a very high temperature. This one have a lot of negative impact because the emission that released during this process, most of them they will produce sulfur dioxide and carbon dioxide, which is air pollutants. Those emissions of sulfuric acid waste, acid rains. So because the smelting process later on, you need to cool the ore. That will include polluted water and not contaminating the water system with toxic. Smelting production of slag, which contains several elements that can cause the pollution to the water. So when you dispose those slag, that particular area is inhabitable. So normally these are the main. Okay. Okay, so generally I think I'll pause here. So you can continue to read the notes for the refined metals and circular economies. Sorry? You can do, there is a review question at the back. That review question includes a little bit about circular economy, but you can read and do it. That will be great, great homeworks for your break. Section 3C and the review questions. Not only review, we have a worksheet 3 and 3.1 and 3. These are all like review questions. So those review questions can be done. All right. Okay, so I'll give you an early break of about 3 minutes, 2 minutes because of holiday. Yeah. So don't forget that